All right. Let's see here. Let's see here. Groovy. This is getting annoying. I gotta find a different solution. So what should we do? What should we play? What music should we play? Come on, give me some good music to play. Alright, this is fine. I don't know what to play. Let's see it. Twinkle, twinkle. Alright. Alright, suckers. What's going on? What is going on? Yo, Blitz and Guild. How's it going, my guy? Welcome back into the stream. Hope you guys are having a great day so far. Welcome back into the stream. Welcome one, welcome all. Okay. I want to try something. Let me know if, I don't know, maybe not, maybe today's not the stream, but try something. Let's not do it, try something. Okay. All right. So today, you guys, we are going to be jumping back into... I'm doing good, my friend. Doing good. All right. We're going to be jumping back into MIT 6.0002, problem set 1. This is part 2, or the problem B of the problem set 1 Space Cow Transportation, which is about kind of like algorithms, greedy algorithms, brute force algorithms, and I'm sure we're going to get into some more here. So yesterday, or last stream, we solved the first part of the MIT 6.0002 course problem set 1. This is like the homework that they were given, right, for the course. So we finished the first part. And we're going to be moving on to the second part of problem set 1, or PS1B.py. So thank you guys so much for being here and joining me tonight. Let me know what you guys are working on and studying here. And if you guys are taking the course as well, let me know that too. I often find it fun to know if anybody else is also doing it. So cool. let's go ahead and dive on into the content for today. Okay, so this is where we left off, right? Oh, interesting. Can I just zoom this? Okay. All right. Okay, here we go. So last time we finished part A, right? We're on part B now. Golden eggs. Oh, this is a different problem? Oh, it's golden eggs. I'll have to rename the stream. My bad. Let's go rename the stream. RIP. Sorry, you guys. Edit video. Thanks for the like, whoever left the like on the stream already. I appreciate you so much. Whoever that was, let me know in chat. I want to shout you out. Alright, let's go ahead and adjust this up. Problem set 1. This is going to be called golden eggs. Problem set 1. Golden eggs. And then we'll remove this guy. All right, we're all good. All right, you guys, let's get into this. This should be fun. Hopefully it's not too hard. Okay. After the yucks. Yuck. It's like a goofy impression. Yuck. After the yucks transport the cows from one of their interns finds flocks of golden geese. Hey Syndicus, how far did you get? Been gone since you did CS50. Oh, nice, man. We built quite a few projects in between then. Our CS50 final project, Small Business Manager. We did Chromaplot, SpectroSim. We built like half of Stalker because we're lazy. We don't want to finish it. And we started a Better Options project. We built a website, personal website. Yeah, we built a lot of quite cool things so far in the kind of short period. I feel like I haven't built like enough, but I have built quite a bit. But I don't know, it's kind of fun. Whatever. What have you been building? Let me know what you've been building. All right. After the yucks transport the cows, one of their interns finds flocks of golden geese. Due to the budget cuts, they are forced to downsize their ship so they can't simply take the geese back, but instead decide to take their golden eggs back. Okay, wow. Their ships can only hold a certain amount of weight and are still very small inside. So because all the eggs are the same size but have different weights, they may want to bring back as few eggs as possible that will fill their ship's weight limit. Because all the eggs are the same size, but they have different weights, they would want to bring as few eggs as possible that fill their ship's weight limit. They would want to bring as few eggs as possible. I'm guessing this part is kind of like, is it kind of arbitrary because all the eggs are the same size, right? So we only really care about, you know, prioritizing lighter. Oh, so maybe you want the heaviest eggs. Oh. Okay. So you want the heaviest eggs then. You wouldn't want lighter eggs to bring as many eggs back. probably because of the size constraint, very small inside. Golden eggs are all the same size, right? But may have different densities. Boom. Thus, 1 2-pound egg is better than 2 1-pound eggs. Thus, 1 2-pound egg is better than 2 1-pound eggs. Yeah, you get the same amount of weight per volume, right? Rather than getting double the volume for the same weight, right? So you want to maximize volume or minimize volume and maximize weight. Do I have that twisted? Dynamic programming, problem B1. Dynamic programming, hatching a plan. The Ayaks want to carry as few eggs as possible on their trip as they don't have a lot of space on their ships. Okay, they want to carry as few eggs as possible because they don't have a lot of space. And they want to carry as few eggs as possible within their weight limits, okay? They have taken detailed notes on the weights of all the eggs that geese can lay in a given flock and how much weight their ships can hold. Implement a dynamic programming algorithm to find the minimum number of eggs needed to make a given weight for a certain ship in DP make weight. So implement a dynamic programming algorithm to find the minimum number of eggs needed, right, to make a given weight for a certain ship. The result should be an integer representing the minimum number of eggs from the flock of geese needed to make the given weight. Your algorithm does not need to return the weight of the eggs, of what the eggs are, right? Just the minimum number of eggs. Okay. A solution that does not use dynamic programming receives 0 points for this problem. Notes. Dynamic programming algorithms will be covered in lecture on October 26th. We already watched that one. If you try using brute force algorithm on this problem, it will take substantially long time. To generate the correct output, there are a large number of egg weights available. You may implement your algorithm using top-down recursive method or bottom-up tabulation method. The former was covered in lecture, but we accept either method, and we went to the top-down recursion. The memo parameter in DP make weight is optional. You may or may not use this parameter depending on your implementation. Assumptions. All the egg weights are unique between different geese, right? But a given goose will always lay the same egg, right? So it always is the same size, but there's different weights. The Ayaks can wait around for these eggs to lay as many as for these geese to lay as many eggs as they need. Okay. Example. Suppose the first ship can carry 99 pounds. Is the music a little too loud? Suppose the first ship can carry 99 pounds and uses the first flock of geese they find, which contains geese that lay eggs with these weights, 1, 5, 10, and 20, right? Your dynamic programming algorithm should return 10. The minimum number of eggs needed, right? So to make 99 pounds is 4 eggs of 20 pounds, 1 egg of 10 pounds, 1 egg of 5 pounds, and 4 eggs of 1 pound. Dynamic programming involves breaking a larger problem into smaller, simpler subproblems, solving the subproblems, and storing their solutions. What are the subproblems in this case? This problem is analogous to the knapsack problem, which you saw in lecture. Okay, cool. So this is our problem here, right? So we're going to write our code here. So the docstring says find number of eggs to bring back using the smallest number of eggs. Assume there is an infinite supply of eggs of each weight and there's always of egg of value 1. So parameters, egg weights is a tuple of integers, available egg weight sorted from smallest to largest value. Okay. Target weight is n. Okay. Into amount of weight we want to find eggs to fit, and memo, dictionary optional parameter for memoization. Okay. So let's think here. Our base case. Let's pull out the old whiteboard here. Yeah, let's do some classic drawing here. Let's talk about this one, guys. Hey Tim. Hey Adalbaran. How's it going? That's a new name I haven't seen in here. Thank you so much for coming in on Twitch, my guy. I appreciate you so much. All right. Oh, are you on YouTube? Oh, you're on Twitch now and YouTube. I'm not sure. Okay. Hey, Dragon. Okay, so let's think here. So we got to think back to the memoization that we did in the lecture. Now, if we do recursive on dp make weight, so our base case is that okay, so this is where recursion always messes me up, always. Come on, like, you got this. Okay, so if I'm going to, I have egg weights and the memo here. So what would I save as the memo? Obviously the eggs used. And the sum, or like, so if, let's think. Okay, so if it returns int, smallest number of eggs. So this is kind of like the CS50 problem of like make change or whatever, where you were given you make change, starting with the largest values and we're going the smallest, right? But we're going to use a recursive approach here, or dynamic programming approach. So, I'm so bad at recursion. My brain just always just goes such a fart mode, man. Okay. Okay, so let's draw it out. If we start off with a weight of 99, right? So we're going to decrement our n value, or our target weight, right? Now you can either take so then we're going to have to loop, right, for like weight in egg weights, right? We're going to call dp underscore make weight, whatever, on the 99, right, less than the weight. And then that's going to recursively go down. So we're going to have a base case of if Well, actually, what we can do, let's back up. Maybe we can optimize it a little bit better. But maybe let's go like this. So this is target weight. Let's take target weight less equals the weight, right? And then we're going to say if target weight is negative, right? We're going to break. Or not break, we're going to, sorry. Would we break? I think we wouldn't want to break because we don't want to we would continue. Right? Now, once we continue, we're going to move on to the next weight to see if, well, actually it goes into increasing order, right? These weights are smallest to largest, they're sorted, so we will actually break because every other weight, smallest to largest. So that means we have to say, and we want to take larger values first. Okay, hold on. So we have a target weight of 99 initially, right? We want to say for every weight in the egg weights, right? We're going to decrement target weight by that weight. No. I don't want to. So then let's set up a base case. Let's just do this. Let's just make it easy on ourselves. Come on, Mike, don't be dumb. Let's just call DP make weights on, right? The target weight less than the weight, right? Now in our base case, we're going to say if the target weight less than 0, right? We're going to break. We don't want to return this value or do something, right? We don't want to or just return Let's think about this. Okay, so what's our base case here, right? If target weight is less than 0, what are we going to do? We're going to return no, because less than 0 is invalid. We don't want to return invalid answers. But if it's equal to, think, Mike. We just did a problem like this on LeetCode. Hey Austin, how's it going, my guy? Okay. So, should we go to our notes? Let's go to our notes. Why don't we go to our notes? Let's be smart. Let's go to our notes. So this is our notes, right? This is the algorithm from our notes. 0 or 1 for the fast fib. So we want to save 35. In the memo, we want to save the value. And then, so in our memo, we would want to save as the key the value of n. But then what would be the value? What would be the value? A set of egg weights that you sum. No, the count of eggs. Yeah, the count of eggs. So we would want to return, if its big case is 0, return 1. That's 1 egg. So on a base case of equals to 0, do we return 1, right? As in, okay, we got 1 egg, right? Now, right? So if we hit the base case of 0, meaning, okay, now we return 1 egg value sum back. Now what we'll do is we need to save, if we don't hit this base case, so initially 99 goes in. So initially 99 is the target weight. 99 doesn't hit this base case, right? Doesn't hit the base case, so then we need to save 99 into the memo. These recursion problems always troll me. Should I go back and look at that leak code problem we solved? We solved that one in like 5 minutes. I don't know why. Come on, Mike. So in this case, in 0 or 1, we return a single value back. So when we hit the base case, 1 becomes here, and 1 becomes here, so it becomes 0. This goes into the memo. Dictionary returns n. Result of the fast fit call at this. Weight equals to 0, we return 1. So then, okay, we do like this. Would we go let's try to access the value of that we're currently on, right? So if memo index of the target weight, right? We're going to return memo index of target weight. Else, right, if we don't have a current target weight that was solved already, right? Because the first, we're going to decrement 99 by 25. So by doing the 5s, 5 times, it'll hit that value. So the target weight will get triggered here into the side of the memo, and we'll return the value that was saved here. Now what we're going to do is say result is equal to, right, and we need to call the min on target weight sorry, the min on DP make weight on target weight, or sorry, on with egg weights, target weight less than no, so we'd have to say like for weight in egg weights but we need to go backwards through this, right? So let's just say for I in the range length, range of, what is it? So if this would be negative 1, 2, 3, 4. Yeah, so it would be negative 1. Start at negative 1, stop at the length of the egg weights, the negative length of the egg weights, right? And then we're gonna have a skip of negative 1. Now this will go from negative 1, negative 1, negative 2, negative 3, negative 4. This is 4, so we need to minus this value by 1. We're going to iterate over the back and say if egg weights, or sorry, if target weight less than egg weights index of I is negative, then we're going to continue, right? Else what we're going to do is call DP make weight on the current egg weights. The target weight is equal to target weight less than egg weights index of I, and memo is equal to the memo currently, right? Now, so this will automatically kick out and pass over weight values that would go past, and so we would never actually recursively call on those negatives not hitting this base case, and we would just skip altogether. Now, the thing is we're not saving though. So at this current weight, at this current target weight in this recursive iteration, right, we're going to say this is going to return a value. So we need to do I, and then do we need to say vals equals to a, we could do a set, and we could just take the we would just do vals dot append DP make weight, right? Or not append, add, and then we could do well, we could make it, rather than returning 1, the weight or whatever, we could make it so that it returns the weights themselves all together, the egg weights, and then we could sum So we say vowels, and then we're going to take so we're going to take memo index of target weight is equal to the min of vowels but we're not summing anywhere actually, so this is wrong. So we're returning 1. Okay, we're going to return I missed it, Tim. So I need to loop over all the egg weights and recursively call down on the weight. Okay, so let's do a recursive tree here and see if we can with a basic example. So let's do 30. So 30 is going to go down 25 to get to 5. It's going to go down 10 in the first call to go to 20. It's going to go down 5 to go down to 25. And then it's going to go down 1, going down to 29. Okay? We saved all these values. So then the 5 is going to try to call 25. It can't do it. It continues. It's going to try to call minus 10. It can't do it. It's going to try to call minus 5. It goes to 0. We hit our base case. We return back 1. We return back my headphones died. Come on. Just want to start the vibe. The headphones died. No. Charge up for like 5 minutes. Okay, we're going to return back 1. Okay, so let's do this. So then actually, if target weight, well, should I handle the negative and then return 0 and then sum? No, I want to call going to save 5. That's not what we want to save. We don't want to save 5. Yeah, we do want to save 5. So we want to save the amount that we're getting, right? So then we're going to update memo. So then we come on, Mike. Come on. You can do recursion. You can do recursion. Okay, so we have a base case. If we hit 0, we return a value of 1, meaning that we have 1. Now we're going to count up. So I have to sum somewhere, though, right? So I'm saving the for this target weight, I'm saving the current value that was found to be here. But these are not returning values. Return 1. So I just need to call dp make weight. I don't want to, I just need to do that, right? dp make weight on right on the egg. It'll pause here. It'll return a result equals to here. Now what do we want to do with this value? Go to 1. We want to add it to the current the minimum result and then return. I don't want to return 5 though. Don't want to return 5. But I need to count for this current egg, right? So I return the base case egg, but I'm never counting for this current egg. So do I add 1 to the current egg, for the current egg to the result? And then do I result dot append vals dot append right, and return the min of vals here? So now 1 is returned back, adds 1, you get 2. Now in the other case, if you had like, no, I've already had like 3. Then you just result here. Return memo target weight here. Heart rate of 99 equals to the minimum value. Let's think here. Let's think. So I am my whiteboard. Right, then this tries to go down by 20. This tries to go down by 25. It can't. Go down by 10. It can. Down by 5. Right. 25. Down by 25. Going to return 1, take by here, add 1, 2. Hey, how's it going, VY? How's it going, my guy? Crap. Okay. I suck at these so bad. Oh. Okay. If memo of target weight. Is this getting hit here right off the jump? It's not even doing anything? 930. Yeah. 99. Here. What? Try. Close. So maybe we just need to return 0 for the first egg. Is that it? Hey. I think we solved it. No? Did we do it? Hey, I think we did it. We got the approval, I think. I think we did it. Yo, come on. Let's go. Let's get the tunes going again. We gotta get the tunes. Let's take this and let's say this. Say, I solved this problem. I think. I am not sure, entirely sure, but I am getting a correct output. What don't show me code. Let's talk through my code. What's the problem really asking? You're trying to minimize the number of eggs needed to hit an exact target weight. You can use unlimited quantities of each weight like coins and you're guaranteed a 1 unit egg. So it's always solvable. This is basically the classic coin change minimum coins problem, but adapted to eggs and weights. You define that if you're at your target 0, then no eggs are needed. So this is the base case for both bottom-out and recursion. Memoization. You're short-circuiting the function if you've already solved this problem. This loops backwards over the egg weights. You're using negative indexing to start the largest weight and go towards the smallest. Skip if over the target. Good guard. You don't want to be subtracting weights that exceed the remaining target. The recursive call and solution binding. Each recursive call says, if I use this egg, what's the best solution for the remaining output? You're adding 1 to the count and storing each possible current egg count in a set. Then later you're calling min on vowels. You're choosing the minimum egg count among all valid paths. Negative indexing is valid, but going forward for weight in reversed eggs might be more clear for readers. So I solved it? What? So I solved it? Yo! Ah! Let's go! Woo! Nice! Oh my goodness. We didn't learn about that one in the lecture. I'm not honestly familiar. We didn't learn about it in the lecture. They didn't talk about it. But the way I solved it in CS50 was just by starting at the weights and just kind of using modulo to get the remaining, and just skipping with if statements, with conditional statements, if the remainder but didn't encompass the magnitude of the weight to be taken out of, basically. Is that what you're talking about? Is that bottom up? I don't know. That's how I solved it in the CS50 one for the coin change. I think we did that one in C, right? Okay, we got to do it right up here. PS2 answers .pi. Oh no, not. Okay. Oh, sorry. PS1B. Okay. Oh, in the same file. Trolling, dude. I'm trolling. What am I doing? Okay, come on. Focus up. Full focus. Come on. Jeez. Okay. Problem B2, write up. Answer the following questions in the same file, ps1 answers.pdf. Okay. Come on, what is it doing? It's trolling me. Okay. Let's try to answer these like we did yesterday. We'll give it a go in our own words. We'll give it some think. We'll discuss it, and then we'll go get some clarity from source. You all know what that source be. You guys think it'll become like cringe? Kind of like pop punk, like not pop punk is not cringe, but do you think like the mentality of pop punk where like it doing things that everybody else does is cringe? Like, do you think that using ChatGPT and AI will eventually become cringe? Bottom up is pretty much asking to do it without recursion. We could do it with looping with modulo to get the remainder, right? And then just using conditionals to decrement based on which one hits first, like which. But the thing is you would have to. You would take the minimum though each time, right? And then save that into an outside variable. We can give it a try. I think it'd be fun. Whatever. Let's go. Let's keep going though. 19 pull 7. I like that. Hey dude, how's it going? If I want to remove overhead, remove the set. My idea with the set was to like not have duplicate numbers. Does that play any purpose really? Like it's not really. I don't know. Like for like. Well, I guess you're only computing what. They're not computing a ton. You're only computing as many like egg weights that you have, right? So I guess it's not really that big of a deal. We could make it a minimum, right? We could set it to like no matter what, we could set it to like just as a safety. We could set it to egg weights, index of -1, right? Because the minimum, the values computed here will always be smaller than this. In theory, I think, right? So then if we wanted to, we could say if right, if result greater than minimum, or sorry, minimum becomes equal to result. And then you can just memo the minimum here. Yeah, that still works too. Right, we don't even need to store all the values we loop through. We can just store them in a variable you getting with the just minimum, right? So now you are saying if we change the target weight, like what if the weight was very large? Like what if target weight was like, yeah, probably it might not work. It's 25. Yeah, so how can we actual output 25. Right. Oh, this is the end of 99. So let's ignore that. Don't listen to that. That's just printed in here. So you do hit, for very large ends, you do actually hit recursion depths, right? Up to 4. So then I wonder, let's change this here. Back to our minimum. And let's change here. You get maximum recursion depth for this one too. Actual output's 405 at 9999. So it is proper to do. So you'd have to have like some very large value. So maybe you set it at n rather, right? Oh crap. Right? You could set it to equal to target weight rather, sorry. And then say right, and then yeah. So if we just have it be the arbitrary large n, I guess it doesn't work for super large n's. That was the largest n you can make here with that one. Interesting. Now what if we make it an infinite flow here? Compute. Now do we get a recursion depth here? Yeah. So it doesn't really matter which one you can use. So I want to see here. Now they do say though, like specifically in the problem, right? I think it's kind of also noted in the problem that there's not that much room on the ship. So if they give it like a value of 99, like pounds, then like having a value of like 9,999 pounds, right? 9,999 pounds. Yeah, like that's a lot bigger than this ship. So I think it's just like for this, I think that's why they're kind of tailoring this recursive depth to this small input size. at least for this type of DP problem, maybe. I don't know. I'm still learning DP here. But let's go ahead and take this approach here. Let's say I removed the set and used the initial as the it also errors in depth past target. Rise works and your changes actually improved in both clarity and efficiency. Pricing the set plus min with minimum variable. You're guaranteed at least one egg, a weight of 1, so every valid target will both be solvable. Initializing minimum equals target weight is safe because in worst case you use all 1s. It avoids the overhead of set and the min call. About the recursive depth target. You're hitting Python's default recursive limit. Since your recursive calls are linear, it might be hit recursively. Only one egg wanted to use, you still exceed the limit quickly. How to fix that? You can set it, okay. Okay, cool. Let's go ahead and do these word problems, or these more thinking conceptual problems. Okay, explain why it would be difficult to use brute force algorithm to solve this problem if there are 30 different egg weights. You do not need to implement a brute force algorithm in order to answer this. If in a scenario, okay, so it would be difficult to use brute force for larger length of egg weights due to the recursive due to the so if there are 30 different egg weights, you would have to loop over all of the egg weights. O of n squared and create and there's no possible order. Why would it be harder? Kay says, any tips in utilizing AI to build projects? I've been using AI to help streamline certain aspects, but always take time to understand what output gave me. I always worry I'm learning incorrectly. You see it kind of how like I'm using it, like just as if you were talking to like a peer or like be honest with it, and with yourself. I don't know. I think it's pretty. It's kind of human nature when you get that feeling when you're going to be in cheat. So if you start to feel that way, it's probably for a reason. But in a reason, I mean like that. You might be like a cheat on yourself. Like you might want to learn it more in depth rather than actually do it. I take a lot of like more pride and more. Not pride, but more like gratification out of actually like typing and doing the thing rather than just getting it done. Like I enjoy the process of it rather than just the final outcome. And people are kind of just focused on final outcomes. Due to the call stack growing increasingly large. Would it be the call stack? Well, that would be for a recursive algorithm. Well, could we use recursive to do brute force? I think so, if you don't use memoization. So it could be due to the call stack. I think it's recursive. Growing increasingly large. Where in a perfect input scenario, you would increase you would call proportionally to the length of egg weights, right? Each loop, each depth. Let's take this and let's go. I'm trying to understand why it would be difficult to use the brute force solution on this. I'm guessing it's meaning to remove the memoization aspect, right? You can have a recursive approach be brute force just by removing kind of the memoization. I'm not exactly super familiar. I'd like to kind of get some more information on that as well. But is my thinking kind of in the right ballpark? I would think that, like, if you... Yeah, let's just have it. Let's talk about it. I think it's better. Mr. Tim, you're absolutely thinking in the right ballpark, and this is great to sharpen your understanding of brute force recursion and memoization and dynamic programming problems like this one. Let's break it down layer by layer. What is brute force in this context? Brute force here means try every possible combination of eggs recursively to try to reach the target weight and take the one that gives the smallest number of eggs. In code terms, this means you do not cache any subproblem results, so even if you already solved the dp make weight 17 once before, you solve it again every single time it shows up in the recursive tree. The recursive tree growth without memoization, let's say 1, 5, and 10, target weight is 12. Each call branch into multiple smaller calls, one for each egg. The number of calls grows exponentially with the target weight because subproblems repeat like crazy. Why brute force is slow? The unique subproblems is small, just like target weight plus 1, but brute force recomputes them repeatedly, many orders of magnitude more than necessary. Let's say you had these egg weights with a target weight of 100. Without memorization, the recursive tree would easily blow up to millions of calls because it keeps exploring redundant paths. Memoization helps because it accesses those saved paths first that we've already done work on. So let's say large because repeated work is done for duplicate inputs. They're removing the cache of That sentence is on the right track. It becomes difficult to use brute force with a larger length of egg whites, or higher target weight because the recursive call stack grows rapidly, and the same subproblems are recomputed many times, leading to exponential time complexity. So let's mention about time complexity increasing the logic because repeated work is done for duplicate inputs, causing exponential. Okay, nice. If you were to implement a greedy algorithm for finding the minimum number of eggs needed, what would the objective function be? What would the constraints be? What strategy would your greedy algorithm follow to pick which coins to take? You know, if you were to implement a greedy algorithm for finding the minimum number of eggs needed, what would the objective function be? Maximize smallest weight every single time. So, objective function would be to maximize or minimize, select the smallest weight on every pass. Right? So objective function. Hey, thanks for the follow, Surah. Thank you so much, my friend. Appreciate you. You're awesome. Thanks for following along, my guy. Start with an objective function. That's the goal, is to be maximized or minimized. Okay, good. We got it right. Select the smallest or minimize the minimum number of eggs the minimum number of eggs needed to fit within something like that. What would the constraints be? So the constraints. Constraints. So the constraint be the weight limit, ship, right? You would have is that it? Which coins to take? Ha! They said which coins. Should say eggs. They totally stole this from the coin problem. They totally copied this. MIT copying problems. Minimum eggs to fit within. What would be the What strategy would trigger the pick to see the minimum number of eggs. So you would need to pick the heaviest eggs first. Those have the most value. Those have the most gold. Yeah, right. So minimum number of eggs needed to fit within, right? To maximize gold weight. / value. Constraints would be the weight limit of the ship, right? Would there be any other constraints for this problem? It's the only thing that really is our limiting is we don't want, we need heavier eggs are more valuable as all eggs are the same size, same volume. Okay, so then our strategy would be sort in reverse order, descending by weight. Sort in decreasing order, we'll say in decreasing order. Sort in descending order and take eggs until you reach take eggs sort in descending order. If the current egg fits in the limit, take the egg. Else, continue on to the next egg until the limit reaches 0 or we run out of eggs. Cool. Let's do that one. Alrighty. I solved this one, I think. How does my verbal answer sound? Nice work. Your verbal answer shows strong intuition. You're very close to clean, accurate, greedy algorithm description. Let's tighten it up for a bit of precision and accuracy. Here. Minimize the number of eggs needed to reach the target weight. So minimize minimum number of golden eggs needed to reach target weight. Okay. Okay, so then constraints. Total egg weight must equal the target weight exactly. Unlimited supply of egg weight. Okay. Oh, there's unlimited supply of eggs. Weight limit of the ship. Heavier eggs or volume. And then unlimited. Always take the heaviest egg that fits within the remaining target weight. Repeat this process until the target weight reaches 0 and no eggs can be added. Well, actually, if each egg is the same volume and the density and the substance is gold, raw gold, then the heavier the egg, the more valuable. Wait. Maybe purity comes into play, but let's assume it's all 10 karat gold. LMAO. We having jokes with ChatGPT. Now you're thinking like a real world greedy designer, a gold smuggler. You're totally right. In real life, if all eggs have the same volume and made of uniform material, let's say 10K gold, then the heaviest egg has the most gold, therefore the most valuable egg per egg. Come on, chat. Step your brain up. Hey, we gained subs like crazy. We gained like 20 subs this stream. Thank you guys so much for joining me here. My name is Michael. I have a degree in human biology and a minor in chemistry. And I work as a formulation chemist for a biotech company where I make biological controls, like advanced analytical controls that are used in like really precise testing for patient diagnostics and things like that. Cross-referencing against valid controls to provide patients proper data. It's kind of like an FDA requirement. So that's the stuff that I build for my company, and I recently just released a big product for my company. We've recent formulation and build and manufacturing, and it was a big success, and everything worked out nice. And so I'm just kind of completing that paperwork for that right now, and I've been teaching myself how to code every single day after my 9-to-5 job as a chemist, trying to learn how to code and implement that into my work, into my life. I built lots of projects. You can find those on my website. I built them completely live on the stream. So thank you guys so much for being here. And if you guys are here, leave a like. It really helps to keep the newcomers coming in. When we get to I think when I get to 3,000 subs, we're gonna have a Counter-Strike 2 gaming stream where we're gonna do some gaming and open up. I think I'm gonna do 30 cases. So we're gonna like 30 cases. Imagine we'll do probably 33 cases for 3,000 subs, right? Or 30 cases for 3,000. Can't do 3,000 cases or 300. That's a little too much, but we'll have some fun and play some Counter-Strike on like a Saturday for a 3K stream, which will be super fun. But yeah, but let's keep going. Okay. So let's see. Hey, you stopped eating. Where am I wrong? You don't need to mention weight limit of the ship. What's the limit? Yeah, you have a weight limit. Hey, nice dude. What are we learning now? Eternity Unknown and Juanez. Thanks for joining me. We're doing MIT's 6.0002 course. We're finishing up. We've watched the first 3 lectures and we're completing the first homework assignment, problem set 1, and then we're moving on to the next couple of lectures. So it's been a great little run so far, you guys. Will a greedy algorithm always return the optimal solution to this problem? Explain why it is optimal, or give an example of when it will not return the optimal solution again. Okay. So will a greedy algorithm always return the optimal solution? I think so. Right? Because you selectively pick out, I mean, you have to loop that many times, m times n times, right? But let's have a discussion about it. Let's have a discussion about whether the greedy algorithm will always produce the optimal solution in this context. My original thinking, or my thinking in general, is that it could possibly produce the optimal solution, or it could always, meaning that you selectively choose or loop n times m times and pick the egg you want each time, where n is the number of eggs and m is the weight limit or optimal weight limit decrements, right? Hopefully I'm making sense, but I don't think I am. You're definitely on the right track. A greedy algorithm produces the optimal solution if the set of eggs satisfies the conical coin system property. This is like US coins. You can always use the greedy approach, take the biggest one that fits at each step, and still reach the fewest number of coins, or eggs in this case, when it fails. The greedy fails when the egg weights don't line up in a way that allows local decisions to build the global minimum. Here's the classic counterexample. 1, 3, and 4. You pick 4. You have a remaining of 2. You pick 1. You pick 1. So 4, 1, 1. Optimal solution, though, is to pick 3 and 3. Oh, it's interesting. Oh. Greedy is locally optimal, not globally optimal. Greedy algorithm assumes that choosing the biggest egg fits will always get you closer to the optimal path, but in some systems, a smaller egg used earlier opens the door to better solutions later. Greedy can't see ahead. Oh, interesting. That's really interesting. Okay, so a greedy algorithm is, what did I say, locally optimal, right? One sec. Gotta make sure my lady hasn't texted me. She's not ready. Okay. Are locally optimal as they, meaning that they do not see ahead. In some systems, taking of eggs, some systems, taking the a smaller value up front, or not taking the largest or most valuable item up front opens up unforeseen possibilities for future outcomes. If you always take the largest egg that you can, there is only one path that can be considered a solution, whereas there could be solutions that are more optimal. I don't know if that makes any sense. Okay, I liked it. A greedy algorithm is locally optimal, meaning it always makes the best decision at each step without considering the broader consequences. This lack of foresight can lead to suboptimal results. In some systems, choosing a smaller or less valuable item early on may unlock better combinations later. If you always select the largest egg that fits, the algorithm follows a single path, potentially missing out on better combinations hidden in search space. Therefore, greedy algorithms may fail to find the globally optimal solution, especially in cases where more than one subsolution exists. It's a really good answer. It's pretty close to mine. Just has a little bit of a, Is local optimal, meaning always makes the best decision at each step without considering the broader consequences. This lack of foresight, meaning that you see ahead in some systems. Should we keep ours or go with the updated one? What do you guys think? Cozy Tink. I want to say that it won't because it chooses the optimal between two given choices, but not necessarily the most optimal overall. Yeah, that's a great idea. Could I have a quick summary of the problem? Yeah, no worries. So we solved this problem a little bit earlier. It's just a dynamic programming problem going over golden eggs. If you've ever solved the LeetCode code problem like coin change, or there's also a problem in the Harvard CS50X course, in their weeks on C that is, I think, called coin or change or something like that, where you also do a similar approach, a similar problem where you just you write an algorithm that gives you the minimum number of objects that can fit within the scope of this constraint, right? So like think of like $1, you can give back 4 quarters. That's the minimum change you can get back with $1. Now things like that. So what this one was just golden eggs rather, and then they each had weights associated with them. Think about like cents, like dollars and cents, right? This gives me a flashback to doing greedy proofs and proving why greedy won't always give globally optimal output. You had to do like actual the proofs behind it. A little bit more difficult approach than just what we're doing here. Just writing a paragraph and being like, yeah, you got to do the formal proof. Bruh. There's a whole mathematical proof behind this. I bet, yeah. That's probably how they kind of figured it out, right? Or like at least validated it in the mathematical field, right? I don't know how that works. I just mix chemicals together. That's what I do. So we'll say we'll change up the strategy. We'll say always take the largest or the heaviest egg that will fit within the limit. Else, continue on to the next egg until the limit reaches 0. Now, I'm going to ask a solution now. In this specific problem, it mentions that it has to, or it's set up to always find a solution that will equate down to a base case of 0. Now, I'm sure there probably are scenarios where you potentially might run into a leftover weight with like a remainder, potentially, that there is no remaining egg or partial egg that will cover, as you can't have partial egg, crack the egg in half, right? You're absolutely right to bring this up. There's a subtle but important nuance of this problem. You're given a list of available weights in grams. There are unlimited eggs of each weight. You want to find the fewest number of eggs to reach the target exact. You cannot use a fraction of an egg as an integer-only problem. The base case is where the target is 0, which trivially requires 0 eggs. Your insight, what if no egg can match the remainder? You're thinking in the right direction. What happens if there's a leftover weight that doesn't match an available egg? Then it's impossible to reach why this problem avoids that. Assumption is the egg weights provided can always be used to make the target. Usually the test inputs are built around this. You're correct if egg, okay, got you. So it's just kind of tailored to this problem, what's it called? Specificality, I don't know, whatever. Let's catch up on some chats. Yeah, if you have those egg weights for 99, instead of a 1, you have a 2, you would end up with a 1 at the end, which is unsolvable. Oh yeah, I got you, Dragon, that's a good point. Nice, dude. Oh, did you transition over from a different field or as well? or did you make the move? Did you make the move? I'm just learning for fun and seeing what happens. I don't really have any like goals for like employment in this field. I just mainly like coding because I like coding. And I like building, I like learning about it, and the math behind it really fascinates me. Honestly, I'm not the biggest proponent of just learning. It's hard to learn math directly. We tried to retake our calculus courses live on the channel, but we only got like 3 lectures in. And then our attention span just started falling off. So it's hard to learn math directly, but when you're learning math with programming, it's a lot of fun, and I really like it, and it's cool. But anyways, you guys, that is assignment number 1, I believe. Let's make sure. Hand in your procedure. Okay, so we just need to make one little correction then to our PS1A. Our PS1A has this down here, so we're gonna write all right, that will satisfy that requirement. We're not going to do this, so I don't need to put my name up there. You can collaborate with people. All right, sweet. That was problem set 1 of MIT 6.0002. That was a lot of fun. I really enjoyed solving these problems with you guys. I definitely got a lot, learned a lot about these algorithms more in depth. It's always good in practice to get more practice with the recursion, man. But yeah, it's always more. We were able to actually really. I'm really proud of myself. We didn't go for any help. We didn't ask. We really just tried to just grind through it, and we worked through on our whiteboard. It's not on here, but we opened up the whiteboard and we drew out a recursive tree and we worked through how we were adding the number back. And I'm really proud that we just kind of put our nose down and just grinded through that and pushed through to an answer. So really, really awesome that we were able to get that one for part B that we did today. But yesterday we did part A, which wasn't too hard. We just had to do a little bit of review on some file IO stuff at the beginning and look up a couple things in the docs regarding the read lines and stuff. And the split, because the data file that was given back to us was also compatible for Windows. So we're getting a \r for return, and I'd never seen that before. So I was trying to figure out what to do with that. And so I just figured out that with some research that we could just use the strip, and the strip will get rid of that as well as the \tabs for kind of Linux and systems and stuff. So pretty cool. Anywho, I appreciate you guys being here and joining me today for problem set 1 of MIT 6.000 Introduction to Computational Thinking and Data Science. I appreciate you guys being here and hanging out with me tonight. Applaud you guys for joining me. Thank you guys so much for the love and all the subs. We're almost to 2730 here. We're at 2727. Ooh, angel number. Bless up. That's a cool number, 2727. Make a wish, y'all. I wish for... what do I wish for? Yes. All right. Got my wish. All right, you guys, leave a like on stream if you had enjoyed the stream here and had a good time. Let me know in the Discord. Oh, join my Discord link down below. It's a complete roadmap for free of all my resources, course, all the breakdown of the course, like weekly breakdowns of like my thinking and like what I thought about the weeks and stuff. I did that for Harvard CS50X, so you can go there and get access to all that and get my notes, the problem sets, and all that stuff in my Discord for free. I don't charge anything for all these notes because I'm getting all this stuff for free myself too. So I like to be authentic like that. So thank you guys so much for being here, and I'll see you guys tomorrow. Let me know if you guys are excited for a potential gaming stream at 3K subs. We'll be opening up some cases and playing Counter-Strike and having some fun. So thank you guys so much, and thanks for supporting. Make sure to like the stream so we can get some more people in here to sub, and we'll get to 3K soon enough. So see you guys then. See you tomorrow, 7 p.m. PST, and we'll be back. We'll probably watch lecture 4 tomorrow. So thank you guys so much for being here, and we'll continue on with the course. Bye, guys. Have a good one.